Rahim students, this is lecture 4 series regarding DC machines, and the first example that we will be solving today is about separately excited DC machines. So for as a brief review, a separately excited DC machine is basically the excitation part is separate and it is a generator, and the armature part is separate. This is the internally generated voltage, this is armature resistance, and as it is a generator, the current is flowing out of the terminal. You can call it VT. And the excitation part, where is the field winding, we apply a certain voltage. There is the field winding resistance, and there is also our adjustable resistance, and there is the current that is flowing into the field winding. And through the KVL equations, we know that VT, terminal voltage, that is the output of generator, is equals to EA minus IA RA. This is the current IA, and in this case IA is also the terminal current that is coming out. And at this side, if we look at what is IF equals to, IF equals to VF over this complete RF. RF is basically equal to RFW, field winding, plus R adjustable. So this is basically a separately excited generator. So here we have the separately excited generator. This is the field part, and this is the armature part, and you can see this is the voltages applied. So the first question is, and these are all the values they have given to us. So if a variable resistor in this generator's field circuit is adjusted to 63 ohms and the generator's prime mover is driving at 1600 rpm, the speed at which the prime mover of the generator is moving, or which the armature is rotating, is 1600 rpm. What is this generator's no load terminal voltage? What will be the no load terminal voltage? No load means that the current output is 0. So how can we solve this? So first of all, in this circuit they have given us a magnetization curve. What is a magnetization curve? It is a relationship between how much field current is flowing, and because of that field current, how much voltage is being generated, that is EA inside the armature. Two fundamental equations that are very critical for DC machines: K phi omega, that is the internally generated voltage relationship with flux and the speed, and the second is torque induced, or torque equals to K phi IA, that is the armature current. So in this for the generator that they have given to us, 172 kilowatt, 430 volts, 400 ampere, and the rated speed is 1800 rpms. And for this they have also given us the magnetization curve. Now remember that this magnetization curve is for 1800 rpm. So they have made this when the generator was rotating at 1800 rpm, the flux was changed as field current was changed, and the voltage that was induced changed relatively. So the only tricky part you can find in this question is they are now saying that you have the characteristics at 1800 rpm, but you are required to calculate the characteristics. This curve is for 1800 rpm, but you are required to calculate it for 1600 rpm. That is the only tricky part. And you can understand this question is not very difficult. So first they are saying that what we do is, in part A, R adjustable is for 63 ohms. Now we know that the total field winding resistance RF would be then RF equals to RF plus R adjustable RFW, that is the resistance of the winding, and that is we know is 20 ohms, and R adjustable is 63 ohms. So the total field winding resistance we will be having is 83 ohms. Now this is 83 ohms. So how much current will be flowing for when we have adjusted this? We know so we have to calculate this current IF. We know the field winding voltage. So the field current that will be flowing for this case will be VF over RF, that is 430 volts divided by 83, and it will become equals to 5.2 amperes. So IF equals to 5.2 amperes. And the question they are asking now is how much is the internal voltage? So automatically you will say, okay, for 5.2 amperes, the field current I have calculated 5.2 amperes. So the voltage should be this volt. Internally generated voltage should be 430 volts. And this is just a coincidence that feed voltage and this voltage is coming same. But so I say, okay, at this case, the field voltage, the voltage induced will be 430 volts. And I say this is my answer, but no. Because this voltage is, I call it rated voltage. This is the rated voltage at 1800 RPM. And what in the question they have asked you 1600 RPM. So how can you do it? So this can be done a very simple unitary method for the speed of for the current when the current 5.2 amperes is flowing. And so when the speed I call 1800 RPM, the voltage is this. Now when the speed is 1600 RPM, I call this the speed that is given. So what will be EA? This is the simple question. Or you would have known that EA, I can take the ratio EA over EA naught equals to N over N naught. Simple unitary method that you would have studied in smaller classes. So the EA will be EA naught into N over N naught. What is N naught? Is the 1800 RPM. What is EA naught? It's 430 volts. What is N is 1600 and this is 1800. So the voltage at lower speed that will be induced into the machine will be simply calculated in this way. That will be 382 volts. So this is the voltage at 1600 RPM. Now the second part of this question states that, okay, what would happen if its voltage, what would its voltage be, that is the terminal voltage, if now what we do is we connect a 300 ampere, a 360 ampere load at the output of this terminal. So if we connect this load, as assume that the generator has compensating winding, this statement means that there is no other effect of armature reaction or the voltage is falling down. So what will be the terminal voltage if we know the load? This is a separately excited generator. So now let's look at what's the second part of the question. And the second part of the question, part B, states that what would be its voltage if the certain load is connected to our generator and the voltage and the load is drawing 360 ampere current. So the terminal current, which is equals to the armature current, is 360 amperes. What will happen to our system? So this can be calculated. What will be the terminal voltage? So B equals to, we know VT equals to EA minus IA RA. So EA we have calculated for 1600 RPM, it is 382 volts. IA, it is told us that 360 ampere load. And the armature resistance, have they given us? Yes, here it is the armature resistance. So it will be 0.05 ohms. So the terminal voltage will become, if we calculate, 364 volts. So this means when the generator is loaded, the voltage at the terminal will fall down from 382 to 364 volts. Okay, the next part, that is the C part, it is talking about the generator does not have any compensating windings. So this is related to armature reaction, and this we will not be considering this scenarios. Now, in the fourth part, it states that what adjustment could be made to the generator to restore its terminal voltage to the value found in part A. So what it is saying is that in the part A you calculated this value EA. In the part A you calculated this value EA is equal to 382 volts, and this value actually was the value, it was here. But when there was no load connected, this value was also at the terminal, because there was no current flowing, so there was no drop. But when you connected a load and it was drawing a current of 360 amperes, then there was a voltage drop here. That is why Vt equals to Ea minus Ia Ra. Now in this part he is saying that I again want my voltage Vt that has dropped from 382 to 364 volts. It dropped down to 364 volts here. I want this voltage to be 382 volts. So if I put the value of Vt, so for the part C, if the value of Vt I want is 382 volts, so how much should be the internally generated voltage? That is the question. So minus Ia Ra. So what I want is the new voltage that should be inside the generator. So at the terminals I can get 382 volts. And this voltage, if I put, I know Ia Ra drop, we know that it is 360 into 0.05. So if I add this voltage will turn out to be 400 volts. So if EA, the internally generated voltage, is raised from 382 to 400 volts, at the output the voltage will be raised from 364 volts to 382 volts. This is our requirement. So the next part is, now how can I raise the voltage, that is EA. Now EA we know is dependent on these three things. These are the three things that can change. These are actually two things. K cannot be changed, it is machine constant. The speed we know is fixed to 1600 rpm. The other thing is flux. So if I can raise the flux, that is through changing IF. How can I change IF? By adjusting the R adjustment resistor. If I can change the flux, I can raise EA. And so the next question is, how do I know what is the relation of flux with EA? That is actually the relation of IF with EA, that is known as magnetization curve. So we have a magnetization curve. Yes, we have a magnetization curve. Here we have IF, and here we have the internally generated voltage. So if now what it is saying that I need 400 volts. So if I change my 400 volts, how much IF should be required to raise the voltage to 400 volt? But students, you have to be very careful here. We should not forget that this EA that we have calculated here is for 1600 rpm, and this graph is for 1800 rpm. So EA at 400, EA equals to 400 volts at 1600 rpm. How much will be this voltage at 1800 rpm? Similar to case A, we have to now calculate this value. And as we have done previously also, we know that EA over EA naught equals to N over N naught, and N is the speed in RPM. So you might be wondering, please remember that omega and N are not same. Omega is always in radian per second and N is always in RPM. And in this formula, EA equals to K phi omega, it is omega, not RPM. But we are not using this formula right now. So we have done this ratio. So EA naught. Now what we have to calculate? EA we have at 1600 RPM, N 1600, N naught 1800. So we have to calculate EA naught at this value. So the value of EA naught will be 450 volts. So at 450 volts, we have to see how much will be the current. So at 450 volts, the current will be this 6.15. So EA equals to 450 volts. At this voltage, IF is equals to 6.15 ampere. This is the current that should flow in our field winding to get 400 volts. That will eventually have 382 volts output at the generator. If you will slowly try to absorb this, this will stop looking as confusing as it sounds. The things are related to each other. So at IF equals to 6.1, so how can I make 6.15 ampere? By using this area of the circuit, we can calculate this value. So this is actually RF equals to VF over IF. So the value of RF would be, what is VF? It is given 430 volts. And what is IF? We have calculated 6.15 amperes. And this will equals to 69.9 ohms. But we know that RF is actually RFW winding plus R adjustable equals to 69 ohms, 69.9 ohms. So RF field winding resistance, that is fixed resistance, we have 20 ohms. So the R adjustable, how much we should select R adjustable? That will then, this is 20 ohms, so this will be equals to 49.9 ohms or approximately equals to 50 ohms. So if we adjust our R adjustable to 50 ohms, this will increase the value of IF, which will increase the flux in the machine, which will raise the EA value to the value that is required. I hope it helps. Thank you.